Okay. Now before I actually share my screen, that calculation you did for the car park exhaust, that was a good exercise, I think, because it got you familiar with the code, and I'm going to try and do this again and again, get you familiar with the code, because this is what dictates what we do, and we have to comply with these codes. And so your calculations were a little bit different, but not much. I think it was less than 10% difference, and that's probably accounted for in maybe the area calculations or the distance calculation for the cars travelling through another level. And those things, can make a difference. So that's probably how it came about. And I hadn't actually looked at the project file, but Philip told me afterwards, I spoke to you last week, that the project was a CFD solution. So you can see that we identified by the duct sizing that the airflow in the design was a lot less than what you'd calculated. And that's because of CFD. And that's the whole point of CFD, is to get the airflow down to a point where the carbon monoxide level is controlled to a satisfactory level, without having to put in all this deemed to satisfy ductwork and fan sizes and all that stuff. So it's got significant cost advantages and running cost advantages by using CFD. So that's quite a common way of going about it. All right, I'll share my screen. So last week we got up to clause 3.9. I think we talked about 3.8, replenishment of exhaust air, which is make-up air balancing, which we've talked about a bit before. So any questions up to date on what we've talked about?
No.
Okay, we'll go on to clause 3.9, combination of exhaust systems. Exhaust air systems that serve different types of enclosures shall be kept separate unless they are of a similar nature. This is straight out of the code. Enclosures that are similar in nature may be served by common exhaust systems and are grouped in table 3.2. So I'll go to that table. We have looked at this once before. So that's an important table that you need to look at from time to time. You might be questioning whether you can combine a garbage room exhaust with a toilet exhaust or something like that, and the answer is basically no, you can't do that. So group 1 is airlocks, bathrooms, change rooms, laundries, locker rooms, those sorts of things that are associated with amenities. So they can be combined. If you've got a cleaner's storeroom adjacent to a bathroom or toilet, they can be combined. That's not a problem. Group 2, areas where food and beverages are prepared or consumed, dining room, dishwashing area, food preparation area, etc. They can be combined. Normally, if we talk generally about a kitchen exhaust system, if you've got a commercial kitchen, you wouldn't normally connect other things to that. So you've got a kitchen hood over the cooking areas, and you'd have a dishwasher normally, which would have a hood over it, and it's required to have a hood to take away the steam. They're normally combined. Sometimes they might be a separate system if it's convenient to do it that way, but most commonly they would be combined into one system. And the other thing to be aware of with kitchens, I know we're not talking about kitchens, but just to put in your memory bank, is that quite often kitchens are a separate fire zone. So they might be enclosed in a fire compartment. So wherever you come out of the kitchen, you've got to be careful that the ductwork is fire rated when it leaves the kitchen. That's not always the case, but just look for that if you're looking at a kitchen exhaust system. And so on. So planned enclosures, number 3, compatible processing closures. So that's just document copying, plan printing, photographic processing, etc. That's common in a, say, an office environment. You might have a printing room where they're printing drawings and things. So that's a separate exhaust system. And photocopiers sometimes have a separate exhaust system, but not absolutely necessary. So we'll move on back to the notes. Exhaust air discharges. All exhaust air shall be discharged to atmosphere in such a manner as not to cause danger or nuisance to occupants in the building, occupants of neighbouring buildings or members of the public. For the purpose of the standard, any of the discharges at the flow rate specified in Table 3.3 shall be deemed to contain objectionable effluent. Now, we talked briefly about Table 3.3. Do you remember that? Objectionable and non-objectionable discharges?
Yeah.
Okay, so that's important to be aware of that, to check that. Generally speaking, objectionable at any flow rate would be things like fume exhausts, dust exhausts, special processes, oil baths, things like that, things that are smelly and potentially noxious or contain dust is objectionable. Non-objectionable is, and also kitchen exhausts above 1,000 litres a second is objectionable. And type B, that was type A, sorry, objectionable. Type B is basically kitchen exhaust systems, which we're not going to cover at this stage because that's a whole different ballgame. So discharges that are not deemed to contain objectionable effluent shall comply with clause 3.10.2. Discharges that are deemed to contain objectionable effluent shall comply with clause 3.10.3. So we'll have a look at those. Page 38. Okay. All right, so this is Table 3.3. Type A effluent, any flow rate. Type B, above 1,000 litres a second. Discharges not deemed objectionable. So we're talking about car park exhaust is not deemed objectionable. Toilet exhausts are not deemed objectionable. And these will be the ones that will be the most common that you deal with. But there will be others. And by the way, I mentioned in the car park exhaust exercise to have a look on the ground floor, or sorry, within the basement area, probably the upper level of the basement levels, whether there were any other areas that you could see would need ventilation. Did you have a look at that at all?
Yes. I wrote down some stuff actually. But it was mainly like the storage and like lobby areas. Is that correct in saying?
Well, any occupied area needs some form of ventilation, but I was really getting at things like garbage rooms, switch rooms, those sorts of areas. Lobbies for lifts, if they're enclosed.
Would fire stairs need?
Fire stairs, well, no, they don't need to be ventilated, but they probably need to be pressurised in the event of a fire. They'd probably have a pressurisation system in them.
Right.
And that in itself is another exercise. We'd have to look at the NCC to determine the requirements for those stairs. Look, as a very general statement, I'll say that stairs that serve a basement car park probably do need stair pressurisation. And that only operates in fire mode. So if there's a fire alarm in the building, the stairs are pressurised to stop or to make it a clear and safe exit for people trying to escape through the stairs and to stop smoke getting into the stairs, okay? So if there's a fire outside the stair, you don't want the smoke to get into the stair where people are trying to escape. So you pressurise the stairs to keep the smoke out. And that's covered in the NCC. And at some point in time, we'll go through that in a bit more detail. Let's keep going with discharges not deemed objectionable. So point A, the discharge shall be located and arranged so that the effects of wind, adjacent structures or other factors don't cause the exhaust airflow rates to be reduced. This is, without the use of CFD or something, it's a little bit hard to really know what's going to happen. But if you know that say in Melbourne, let's say the predominant winds are from the south. I know you get winds from the north, but if the predominant wind direction is south and or north, then you're probably not going to face your exhaust in that direction, because if the wind's blowing, it's going to be hard, it's going to create a pressure, and the exhaust is going to struggle to actually discharge against that prevailing wind. So you'd face it the other way. It's just using your noggin to sort of come up with the best solution. In some cases, we've done exhausts where it discharges in two directions, because so it comes up to like a T discharge and discharges in both directions, because if the wind's blowing from one direction, the exhaust can still go out the other direction. And if the wind is blowing in the same direction as the exhaust, it creates a venturi, which helps the exhaust to operate. So that's just using your common sense in the absence of using CFD or something. The discharge shall not be less than the distance given in table 3.4 from any outdoor air intake, natural ventilation device or opening. So this is table 3.4. This is quite important, and you'll find that this is very useful. Where you have a toilet exhaust in particular, or any exhaust, but toilet exhaust would be the most common, and an outside air intake for the building. Depending on these flow rates on the left column, it tells you how far they have to be separated. Now, prior to this standard being released, in the previous edition of this standard, regardless of flow rates, it was a 6 metre separation. And that's not easy to achieve. And so there was a lot of discussion about this and said, well, does it really need to be 6 metres in all cases? So this table was developed to give you some concessions on that separation. So if you've got an exhaust, let's say it's a toilet exhaust coming out of the building, and you've got an outside air intake for the office part of the building or for some other area, depending on the flow rate, that's the separation that you must comply with. Now, I've highlighted a note in green below the table. For airflow rates less than 200 litres a second, separation of discharge from natural ventilation openings within the same sole occupancy unit do not apply. What that means is if you're doing a residential apartment, which you probably will do quite a bit of, quite often and nearly all the time, the discharge from the bathrooms is out over the balconies of the apartment. So rather than taking it all the way up to the top of the building and discharging at the top, you can discharge it horizontally at the location of the apartment, usually over the balcony. And the ventilation air or the outside air coming in is quite often coming from the balcony with doors. So I'll have a door open, but you've got a bathroom exhaust. So what that's saying is, for flow rates less than 200 litres a second, which it normally would be, that table doesn't apply. Oh, my mouse just went to sleep. Sorry, I'm going to just try it again. We're back on. Okay. So that's an important table to be aware of and to use. You'll use that a lot. Now, point C, the discharge shall be emitted to the outside at velocities and in a direction that will ensure, to the extent practicable, no danger to health or prevent a nuisance from occurring. So again, common sense. Don't face it into the wind. Don't blow it straight into a location where people are going to stand if you can avoid it. But there's always there's always concessions that can be made if you can argue sensibly. So D, the discharge shall be not less than the distance given in table 3.4, which we just talked about, from the property boundary, except that where the dimensions of the property make this impossible, then the greatest possible distance shall apply. So what does that mean? That means if you can't comply with the code, then maybe you don't have to. So it's one of those things that's a little bit hard to fathom, but what you'll find is in some cases, you might have a very tight site, and to achieve the distances required by this code, you may not be able to do it. So the aim is you always try and comply with that table. If you can't do it, you find the most sensible location you can. And if you're convinced that it's not going to be a nuisance or a hazard, then you can do that. So that can be argued. There's a few notes there that you might like to read through, but we won't go through that now. Now, discharge is deemed objectionable. So these are the nasty ones from laboratories or from welding bays or dust extraction systems, that sort of thing. It could be hazardous to breathe in this air. So what we're saying is objectionable is it's a hazard to us breathing the air. Okay, it might be noxious, particularly from a lab. You might be breathing in fumes that could be potentially life-threatening. So this is serious stuff, and it might pollute the environment as well when on the discharge. So air discharges that are deemed to contain objectionable effluent shall be in accordance with clause 310(2) and, which was the previous one. Now, in this case, they must be arranged vertically with discharge velocities not less than 5 metres per second. So for non-objectionable, they don't have to be a vertical discharge. They can be a horizontal discharge. So for a car park exhaust, you can discharge out into the street with a horizontal discharge. But if it's deemed to be noxious, it used to be called noxious, it's now called objectionable. It's got to be vertical, and it's got to be not less than 5 metres a second. Now, point 1 here, for type A effluent, which is the bad stuff, the discharge must be at least 3 metres above the roof at the point of discharge, except that in the case of a pitched roof, at least 1 metre above the ridge. So what we're talking about here is you may have seen, driving past a hospital, you might have seen all the exhaust stacks going up in a bunch of stacks. Have you ever noticed that? Bunch of exhaust flues that go up above the roof. Well, when you drive past them, the more you work in this business, the more you'll start looking at buildings and saying, oh, okay, I can see why they've done that. Or you walk into say an office space and you look up and you look at how they've located the diffusers and all those things. It just becomes second nature after a while that you start to develop this interest on how they do things and relate it back to what we're talking about. So a hospital is a good example, or you've got rooms that are laboratories in a hospital that are exhausting dangerous discharges. Laboratories are the same. Industrial buildings. So what that means is when the flue comes through the roof, the exhaust flue, if the roof is trafficable, which means if people can actually go up there and service fans and things on the roof, then the discharge has to be 3 metres above the roof. So that it has to be vertical, so that anyone working up there is not likely to be in danger of inhaling these dangerous fumes.
Peter, are you allowed to combine if you've got several fume hoods or several of these flues? Can you combine them?
Yes, you can. It's common not to, because they like say if you've got a lab in a university where you've got a whole lot of fume cupboards, for instance, normally you run those separately because they can operate independently. So it's normal to have a separate discharge for each one. I worked on a lab at Monash Uni that had something like 70 fume cupboards in the building. It was the chemistry building in the engineering faculty, actually. They call it the green chemistry building. You know that one? You went to Monash, didn't you?
Chemical Futures, I think. It's the
Yeah.
the beehive building we also used to call it because it's kind of shaped like with those hexagons.
Yeah.
It's a cool building.
Well, I worked on that with A.E. Smith, and Philip did too, actually. That had something like 70 fume cupboards, and they were all ducted separately to the discharge. So that was quite a job. So we had 70 exhaust flues going up through the building, up through the roof. But you can combine them. There are special systems that are available, and we have done them. They're not very common. They're extremely expensive, and subject to quite a bit of regulation as to how you do it. But the simple answer is yes, you can, but it's not normally done that way. Now, okay, so next one. The discharge has to be above any part of the building or an adjacent building that is within 15 metres horizontally of the discharge point. So let's say you just take one building. Let's say it's a laboratory. You've got some flues coming up through the roof, but there's another part of the building that's actually higher than the main roof. So if it's within 15 metres of the discharge point, then the flues have to go up even higher above that. And this is what I just said before, at least 3 metres above a thoroughfare or roof subject to regular traffic, up within 15 metres of the discharge point. Excuse me. Now this next one, C, located not less than 6 metres from a property boundary, any boundary to a public street, any outdoor air intake opening, or any natural ventilation device or opening. So this is the old clause that used to apply to all discharges, that it has to be at least 6 metres away from any boundaries or outside air intakes. They've relaxed that now for non-objectionable discharges, as I said just before. So it's understanding that distinction between the two.
Peter, just on the previous point, B3, just above, at least 3 metres above a thoroughfare or roof subject to regular traffic, but within 15 metres of the discharge point. What's that discharge point there? What does that refer to? Because I thought this is talking about the locations of the air discharges.
Yeah, that's a bit.
Is that like the source of the fumes? Like,
so we're talking about the discharges. So we're going back to the start. So they shall be in accordance with 3.2, and so B, for a type A effluent, be situated at least 3 metres above a. So that's what I was just talking about. So it's got, if you've got people walking around, it's got to be 3 metres above the roof, but within 15 metres of the discharge point.
Yeah, it's that part that.
Yeah, that's.
I don't understand.
Yeah, well, the previous one was it's got to be higher than any other part of the building that's within 15 metres. At least not within the.
Yeah, like what is the discharge point? Is that like air discharges?
At least within 15 metres of discharge. I'm not sure. At least 3 metres above a thoroughfare or roof, subject to but within 15 metres. Yeah, I'm not actually sure what that means. There might be a bit of a grammatical error there, I think.
Mm.
Because I think really the important one is going back to the 2, being 15 metres away from a part of the building that's higher.
I thought maybe it's like the source of the fume cupboard or something. Like, could you run one of these flues like 20 meters up a building? You know, like, is there any limit to how long you can run that to the roof?
No. That comes back to your calculations of fan static pressure. So you can run it. You can have a building that's 20 stories high and run the exhaust from the ground floor. You just have to size the fan to be able to operate against that resistance.
Yeah. Okay. Yeah. So it's a bit confusing then, the wording.
So yeah, I actually don't know what that means. Sorry. Yeah. It's probably not something that I've ever come across to try and analyse that, to be honest. But no, sometimes they do make grammatical errors, and sometimes they get words wrong or they leave words out, and that can really throw you sometimes, particularly with the NCC. The NCC is a very kind of academic document in some ways, and very subject to interpretation. So we as engineers have to use our common sense sometimes, or if there's some way of analysing it, we can do that. But with experience, you sort of know what the answer should be, and you refer back to the performance objectives. What are we trying to achieve? In this case, we're trying to achieve a safe discharge so that people can operate around the discharge points of these flues. And some of the words can be confusing. But safety is number one. Safety of personnel and the building is the key. Sorry, I couldn't clarify that a bit better for you. Point D, if necessary, treated to reduce the concentration of contaminants. So this is not common, but if you've got an exhaust, and one that comes to mind would be from a laboratory in a hospital, for instance, or a lab in a research place that is discharging toxic gases that are potentially dangerous to humans and potentially life-threatening. This could happen. Sometimes they use HEPA filters in the discharge to reduce those contaminants before they get discharged into the air. It also might apply to, say, a coal-fired power station. Discharging, it's not quite relevant to what we do, I suppose, so maybe that's not a good example. I can think of another one. I did a job in Sydney once that had a Ritz-Carlton hotel in Sydney. And Ritz-Carlton, an American company, have their standards for how they want their public areas to be fitted out. And they like to have wood-burning fireplaces in their hotels. Now, this is something that we would never do in Australia, but they insisted on it, and it took them a long time, but they convinced the council that they had to have that. So we had 3 areas, lounge areas, where we had open fireplaces, burning wood. So you know what a fireplace is like, the smoke that comes out of it and the smell. So we had to install exhaust systems for each of these fires, not just a chimney, because it was a 6-story building or something. We had to actually duct the fumes, the smoke out of the fireplaces, and we did that with steel pipe. But we weren't allowed to discharge smoke into the air. The council wouldn't allow that. And in where this building was located, it was in Double Bay. It's kind of a valley area, very low. So they didn't want smoke and smells going out into the air in that area, because it would have affected the the residents around there. So we had to put in electrostatic precipitators, and they removed the smoke and the smell. And so the discharge to the air was relatively clean. So that's just an example of what might happen. Pretty rare, but that's an example. So as that note says, note 1, item D may be necessary where the ambient air is liable to be significantly polluted by the discharge. Reference to relevant authorities is recommended for control requirements relating to concentration of contaminants. So, you know, if you've got a really nasty discharge, it's likely that the EPA will be involved, the local council, maybe even the state authorities. But in what we do, that's not very common. Okay, let's just go back. So that's all those points there. 310.4, non-required discharges. So going back to the standard again, this is another one that you'll come across. Have you done anything yet with ERVs?
No.
So an ERV, that's another abbreviation, is an energy recovery ventilator. It's basically it's a system with a fan in it, fan and filters, but it's got a heat exchanger. So what it does is when you bring in outside air, to reduce the energy impact of the outside air, you exchange heat with an exhaust air stream from the space. And so you pre-cool and pre-dehumidify the incoming outside air. And because the air that's being exhausted generally is just room air, it's not contaminated. So these rules of distances between intakes and exhausts are not relevant. And if you have an economy cycle where you're bringing in full outside air because it's cool enough to provide the air conditioning or to cater for the air conditioning load without using refrigeration, that's an energy saving feature. The discharge, so if you bring in 100% outside air, you have to get rid of it. You can't just leave it there. It's got to be exhausted out or relieved out of the space in some way. The distance between the intake and the discharge in that case is not governed by the code because the discharge is not objectionable, and it's, you know, it hasn't got any smells in it. It's just hot air that you want to get rid of. So I'll just quickly read through that. Spill air and relief air. This is what they class as a non-required discharge. Spill air and relief air shall be discharged to atmosphere in such a manner as not to cause nuisance to occupants in the building, occupants of neighbouring buildings or members of the public. That's the same thing they said before. Where air that has ventilated enclosures within the building is discharged from the building, it may be redirected to re-enter the ventilation system, provided the net inflow of uncontaminated outdoor air is not less than that required by Section 2. You can go and read all that, but if you look at the commentary, this provision allows a non-required air discharge point to be located. When they say non-required air discharge, it's not a required exhaust system, okay? It's just a relief air system. You're getting rid of the air because you're bringing more air in. You're doing the air balance thing, okay? This allows a non-required air discharge point to be located closer to an outdoor air intake point than would be allowed for a required exhaust air discharge point, and would apply to non-required design provisions such as those applied to an economy air cycle. So economy cycle or ERV. The difference between the economy cycle is normally an economy cycle is 100% outside air. So you're using outside air for cooling and not having to run refrigeration. And an ERV is a smaller system that's just preconditioning outside air. And when you're working through CAML, you'll see there's a tab there for preconditioners. Have you noticed that at all at this stage?
No.
Okay.
No, we haven't used Camel yet. I mean, I used the old desktop version several years ago, briefly, and we haven't really got stuck into it yet.
So when you're doing the inputs for the calculations, there's a tab there that'll ask you if there are any preconditioners. A preconditioner is an ERV, basically. So if you're preconditioning the outside air, so Camel needs to know that, because if you ignore that or say no, there aren't any, then Camel assumes that the outside air coming into the space is at ambient conditions, so temperature and humidity of the ambient air. If you have a preconditioner, then you're actually reducing the temperature and the humidity of, well, sorry, I should say temperature and moisture content of the outside air. And that's going to reduce the heat load in the space or on the air conditioning equipment. So that's, just be aware of that. That's what a preconditioner is. It's an ERV in simple terms. Okay, I just wanted to mention section 5 of AS 1668 part 2. This is mechanical ventilation for healthcare functions. This section sets out minimum requirements for ventilation rates for hospitals. We'll just have a quick look at it. Sorry. Right, so can read all the preamble there, but so it talks about areas such as operating rooms, outdoor air rates, air change rate, supply air filtration, etc. Room air pressure. So all those things are important. An operating theatre is a good example. So this gives you a certain air change rate. It says here you need at least 20 air changes an hour. Minimum outdoor airflow rate shall be the greater of 20 litres a second per person, or 10 air changes an hour. Filtration talks about what sort of filtration you need in the air conditioning system. Quite often, and just about always, an operating theatre will have final filters behind the air diffusers. So they'll have HEPA filters actually in the operating theatre, so that when it air's discharged through there, it takes out any dust that's picked up between the air handling equipment and the room. And room air pressure, the air pressure in an operating theatre is always higher than surrounding areas. So you do that by your air balance. And if you're looking at an operating suite where you have several operating theatres and then surrounding areas, you've got to do a pressure balance calculation. So you have, say, 30 pascals in the operating theatre. The corridors outside might be at 20 pascals. Other areas might be at 10 pascals, so that you've got a cascading effect of the air. The air's going away from the operating theatre. You've got no air leaking into the operating theatre because you don't want to bring in contaminants into the operating theatre. So that's what this is talking about. A sterile store is pretty similar to an operating theatre normally. Infectious isolation rooms, they can be positive or negative pressure depending on whether you're trying to isolate a patient or you're trying to protect them from the surroundings. So if it's negative, you don't want their diseases to get out of that room. If they're being protected in a positive room, you don't want anything from outside to get into that room. So these are all things that gives you information. Now, I just wanted to mention here that don't take this as gospel, because if you're doing a hospital in particular, every state has its own code. Unfortunately, as far as I'm aware, or last time I looked anyway, which was probably last year, every state has its own standards. They're quite similar, but they could be different. So and it'll set out, there'll be tables. Victoria has one. I've got the details here if you're ever looking for it, but you guys have got it in your files. They will have their own standards for operating theatres, for isolation rooms, for sterile stores, for sterile cleaning areas. So they're the ones you really need to refer to, the state standards. And AS 1668 Part 2, if something's not shown in the state standards, then you can refer back to AS 1668 Part 2. Okay, so you just need to refer to both if you're doing a healthcare job. Having said that, that's a hospital. Hospitals are very highly regulated, obviously. But if you're doing like a medical centre, and you ask them for their design standards, they'll probably say, "What do you mean?" They don't know. So if they have these rooms, they'll have procedure rooms. They may have procedure rooms. They might have sterile rooms. Then you need to go back to AS 1668 Part 2. Okay, so that's where you would use it in the absence of a standard governing the project. So local state health standard. That makes sense. Sorry, I'm rambling on a bit, but I just wanted to make the point that if it's a hospital, this may not apply. It might be the same, but it might not. So you need to use the state health department standards.
Do the hospital design standards have to satisfy this? Like, at least this is the minimum. They may be more strict, but they have to still satisfy this, or it could just be a totally different set.
It's a good question. Generally, the state health department standards will be at least equal to the 1668 Part 2. So you have to take and if they're higher, for instance, have a look at operating rooms. That's a good example. It says here, supply air change rate shall be not less than that calculated to achieve 20 air changes per hour. You'll find that most hospitals, and I have done a lot of hospitals actually, but mainly in Queensland, their standard is 30 air changes per hour. That's the air change rate. Minimum outside airflow rate, 20 litres a second per person, or 10 air changes per hour. That's probably pretty standard. But some states might want you to provide 100% outside air to an operating theatre. I have seen that. Maybe that was in New South Wales, but don't quote me. The supply air filtration, that's pretty standard. You have to use HEPA filters. Operating theatres are a special case, and look, if you do hospitals, you'll be doing operating theatres, and they're very highly regulated, and you need to make sure that you're looking at the right information. And room air pressure, well, this goes through it says the pressure differentials across doors shall be such that the force to open any door against the combined effect of the air pressure differential and any self-closing mechanism does not exceed 110 newtons. And this is exactly the same wording almost as what you see in the stair pressurisation standards. And the 110 newtons equates to about 50 pascals for a standard door. And there's a bit of background to this. 50 pascals is about the maximum that a person who's not very strong, so an elderly person, for instance, can't open a door if it's greater than 50 Pascal differential. That's where that comes from. And it's the same wording pretty much in the stair pressurisation code. So if, like I said before, with the stair pressurisation system, if there's a fire and someone needs to escape from the space that's on fire into the fire stair, then you can't maintain a pressure above I'll say 50 pascals, which it is what it is in the code, in the stair, because an elderly person or a frail person won't be able to open the door. So they won't be able to escape. So that's where that comes from. But you'll find that in the state health standards, it's usually 30 pascals for an operating theatre. I don't think I've ever seen it higher than that. So you'll maintain the operating theatre 30 pascals above anything that's adjacent to it. Okay. Anyway, so I've probably said enough about that. Just to be aware, if you're doing a health care job, and the same with any job really, but make sure you get any relevant design standards together before you start using AS 1668 Part 2. And if those standards don't exist, well then use 1668 Part 2. But talk to your colleagues before you launch into it to make sure you're on the right track, because you might waste a lot of time using the wrong information. So I've probably just confused you with all that, but I'm just trying to give an awareness. It's 10:20, so we'll just quickly go through this. Did you have a chance to look at this at all? I sent out a supplement to the ventilation notes, and this is regarding removal of heat. So we often use ventilation air, whether it's air from outside or air from adjacent space, to control the temperature of a space that needs to be controlled. So some ventilated rooms require control of space temperature to enable the equipment in the room to operate satisfactorily without overheating. So some examples are there: the lift motor rooms, substations, switch rooms, fire pump rooms, generator rooms. These sort of rooms quite often, and the one you probably come across most would be a lift motor room or a switch room, where the lift motor room in particular, there is an Australian standard. I think it's AS 1735 from memory, which actually spells out the temperature, the maximum temperature you can have in the lift motor room. Okay. So if you need to ventilate a lift motor room, there's a couple of ways you can do it. You can use outside air to take the heat out and to keep the temperature down, or you can air condition it. In Queensland, lift motor rooms are nearly always air conditioned these days, so you're not bringing in outside air. But in Victoria, I think they generally would use outside air because it's cheaper to do that. So when you're providing ventilation to these rooms, and the example I give later on is for a lift motor room, you need to determine the following design criteria. So we need to work out the sensible heat load in the room, including the equipment. So all the equipment's giving off some heat into the room, and you need to find that out from the manufacturers, what the heat dissipated by the machinery is. So with a lift, there's lift motors and of a certain kilowatt rating, and they will have an efficiency, and there'll be heat discharged into the room. There's heat to do the work of pulling the lift car up and down, but there's heat generated into the room, which we have to remove. But also the room itself, it'll have a roof over it, possibly. It'll be at the top of the building, so there'll be a heat load through the roof and the walls from outside. So that needs to be taken into account, and that's basically on any other equipment in the room to work. So we work out the sensible heat load. We need to determine the maximum allowable room temperature. As I said, for lift, the lift code dictates the maximum allowable temperature in the room. If it's a generator room, and I have done these, where the generator people, the suppliers of the generators, will say, we don't want to exceed, say, 50 degrees Celsius. They might say that the generator will operate, because it's normally a diesel engine driving an electric generator. So the engine might operate up to 70 degrees, and it'll probably derate, but it'll still operate. But to have optimum operation, they probably don't want you to exceed, say, 50 degrees So that's a couple of examples. And if you're using outside air, which is normally the case, you need to know the ambient design temperature. Now for Melbourne, it's 35 degrees. Okay, and that's in the error codes if you want to look those things up. So with reference to the aerotechnical manual heat transfer equations, the equation for sensible heat transfer is, and this is an equation that you're going to see over and over again throughout your career in this business. Sensible heat is 1.213 times the litres per second of air times the temperature differential. So we want to calculate how much air we need to remove the sensible heat and maintain the required room temperature. So rearranging that equation, the airflow in litres per second is the sensible heat divided by 1.213 times the delta T. And just, I think I sent you this extract from the aerotechnical manual. Did you see that? Did I send that to you?
Yeah, it was in the email.
This manual has got everything, well, I won't say everything. It's got just about everything you need to know about all these calculations and things. It's a fantastic reference, and get used to looking at it and using it as you go through things, because it's got a lot of good information in it. And the aero design guides, the DA manuals. So these equations are in here. There's latent heat. When you're getting into, after you've done heat load calculations, if you need to do any manual calculations when you're looking at psychrometrics, which we'll talk about down the track, this has got the latent heat calculations, the sensible heat calculations, total heat calculations. Basically, Camel does all that for you anyway. But if you want to check something, you can use these equations. They're quite useful. So back to our exercise here. Delta T, as I said, is the maximum temperature rise allowable for the ventilating air, which is normally outside air, to achieve the room design temperature. So if it's coming in at 35 and you want to achieve 40 in the room, what's your delta T?
5, right?
Yeah, so we're going from 35 to 40, okay? So that's the maximum that you can allow the temperature to rise. And that delta T is then going to dictate the airflow. So I gave you a little exercise here, which you probably haven't looked at yet, but a lift motor room has a peak sensible heat load of 12 kilowatts. So I've just guessed. Last time I did one, we used to allow about 5 kilowatts per lift car. So each car has its own motor. And so in this case, it might be only 2 lifts, 2 motors with the cables that lift the cars up and drop them down. And then I've allowed another couple of kilowatts for the room itself. The lift code requires that the room temperature does not exceed 40 degrees C. Don't take that for gospel. If you're actually doing a lift motor room, you need to look at the code, because I think it might be 38 degrees C, but I just said 40 because that was a nice round number. Ambient air is used to ventilate and remove heat from the room in order to maintain the room temperature below the limit. The ambient design dry bulb is 35. So we've got a delta T of 5, got a heat load of 12 kilowatts, which is 12,000 watts, because this sensible heat here is in watts, okay? So it's a simple calculation. What airflow is required to maintain the room temperature at full load? So if the lifts are operating, and so the motors are generating the most heat dissipation, it's a hot day, so the room is quite warm. What's that calculation? So it's 12,000 divided by 1.213 divided by 5, whatever that is. I haven't done the calculation. That would be the answer. The answer is a big number, isn't it? It's a fair bit of air. well, 12 divided by 5 is, it's over 2,000, say 2,500 litres a second, something like that. That's a lot of air, which you've got to bring in and discharge out again. But it's the most economical and the cheapest capital cost for an area like Melbourne, which it doesn't have the high humidity or the high temperatures all the time.
Are there any rules about like where you have to discharge that heat? Like, could you just, blow air through the room, like through the lift room, and just the heat will just then go into the surrounding spaces? Is that?
No, you have to discharge it back outside again.
Okay.
But it's a non-objectionable discharge because all you're doing is removing heat. If you're doing, so like we talked about ventilation, you bring air in one side and you discharge it out the other if you can. That's cross-flow ventilation is what you're trying to achieve. You want to remove the heat from the motors. So you want the air to flow over the motors and then discharge out, if you can, at the opposite side of the room or through the roof. Usually a lift motor room sits up at the top, above the roof of a building because it's a box on top. The lifts have got to, travel all the way to the top of the building. So you can usually bring air in one side and discharge it out the other side or through the roof, but not back into the building. It's got to go outside. But you don't have to comply with the objectionable discharge requirements. So does that answer your question?
Yeah.
The second question I had there is, do you have any suggestions for ventilation control when the sensible heat load is less than the peak load? So part load operation, which is, peak load is about 1% of the time. So the rest of the time it's in part load between no load and 100%, or 99% if you like. Any thoughts? We'll just finish with thoughts on this. Well, I'll give you a couple of things. And this is what's with the lift code. If it's a lift motor room, the lift code has other requirements. If the temperature exceeds the specified design temperature, and let's say in this case it's 40 degrees, alarm bells start going off. You have to have an alarm down in the foyer of the building, at the entrance to the building, to alert someone in the building that the temperature in the lift motor room is too high, because that could be a problem. If the if the lift motors start to break down or the controls start to break down because the temperature is too high, you've got a problem in the building. So that needs to be raised through an alarm, and that's all spelled out in the code. But if the lifts are only operating intermittently, it's a cold day or not a hot day anyway, so there's not a big heat load on the space, you don't need to run the ventilation all the time. So you can switch it off. So you can have a thermostat, and you would have a thermostat in the lift motor room, which is sensing the temperature in the space. If it's below 40 degrees, and you'd allow some safety, so if, let's say it drops to 38 degrees, then you might either slow the fan down. The fan might have a variable speed drive so you can slow it down. And then if it keeps dropping, let's say it drops to 35 or even less, just turn it off. So you don't have to run it if you don't need it to be running. And this applies to other spaces that they want to control the temperature. It might be just a storeroom where they're storing things where they don't want it to get too hot because it might start to affect what they're storing. So you have a temperature controlled ventilation system, which under full load, to maintain the temperature that they want in the space, you have the fan running using outside air. In some cases, it might be make-up air from adjacent spaces, which is going to be pre-cooled. If you've got that air available, you would use that. So let's say you've got an air-conditioned office space, which is being controlled at 23, 24 degrees. and you've got a storeroom that's got paper in it that they want to maintain at a certain temperature, whatever it may be, then just use, if you've got excess air available, use that air from that space and then discharge it outside somewhere. So the point there is temperature control. You can switch the fan off or change the speed, reduce the speed of the fan to maintain the temperature in the space. Does that make sense?
Yeah.
Yeah.
So you'll find that that's a common thing. It's going to come up again and again, not just for lift motor rooms, but for different spaces that you need to control the temperature. All right. Well, I hope that's been of some help to you. These are the things I'm talking about. I know I'm skipping over a lot of stuff, but I'm talking to you about things that are going to come up again and again, just for you to be aware of it and where to go and find this stuff in the code if you need to refer to it. And I'm going to sound like a broken record talking about codes, but it rules our life in this business that we have to comply with what's in there. We have to get to know what's in there. So next week, sorry, it's 10:36. I better let you go, but just finally, did Philip talk to you about that car park exhaust exercise at all?
No, he mentioned to me that, yeah, like we got similar sort of results, so we're probably on the right track.
Yeah.
But yeah, nothing further.
What would be a good question to ask him, and he might have to go away and find out, but what was the actual design exhaust airflow, just to give you an idea of what the difference is when you use CFD? Because that, and I'm not saying use that as a benchmark, just for that particular project, it might have been reduced to say 35,000 litres a second instead of, what'd you get, 49,000 or something like that? It was high 40s, yeah. So you can see that that's a significant difference. So any ductwork is much smaller, fans are smaller, and the running cost for the fans is a lot lower. So that's the benefit. Now maybe next week we'll be talking about pump pressure calcs. I have got something prepared, but I think, did I send you that? I think I did, didn't I?
Yeah.
Yeah. So before we have that session, have a look at that if you've got time. Otherwise, we'll just go through it. But we won't get into that until Philip's confirmed to me that he's covered what he wants to with you on pipe sizing and those things. So that you're sort of prepared for it anyway. Okay. And if we're not doing that, I have got other stuff ready. I've got air filters I want to talk to you about. Another exciting topic, but very important. All right. All the best.
Thanks a lot, Peter.
See you next week. Okay.
See ya.
Bye.
Yeah.